Hey everyone, welcome back to the channel. Today we're diving into something really exciting. We're going to see if Google's newest AI model, Gemma3, can count solar panels from aerial imagery. Imagine if we could automatically survey neighborhoods and count renewable energy installations without manual labor. That's the promise of computer vision in sustainability tracking, and today we'll see if Gemma is up to the task. This is the second episode in our series on the Lacuna Solar Survey Challenge. If you missed the first one where I walked through Zillow40's top-performing solution, make sure to check it out after this video. So what are we doing today? Well, we're taking Google's Gemma3 4B model, which is their smaller instruction-tuned visual language model, and seeing how well it performs on a real-world task without any fine-tuning. Just prompting. Think of it as putting a fresh graduate on the job without any additional training. Let's see what they can do. Let's start by looking at our notebook. At the top, you can see we're importing the necessary dependencies. We're installing the Transformers library with support for Gemma3 and checking our GPU setup. We've got two Tesla T4s to work with, not the most powerful, but they'll do the job. Next, we're exploring our dataset. The Lacuna Solar Survey Challenge is all about counting solar panels from aerial imagery. The training data has information like image ID, whether it's from a drone or satellite, the placement type, and most importantly, the number of panels in each image. Looking at our sample, we have 18 images with varying numbers of solar panels, ranging from just one panel to a whopping 350 panels in a single image. That's quite a range. Some images are from drones with the label D, and others are from satellites with the label S. The placement can be on roofs or in open spaces. Now, let's set up our Gemma pipeline. We're loading the model with image text-to-text capability, which means it can look at an image, read a text prompt, and generate a text response. We're running it on GPU with bfloat 16 precision to speed things up. The interesting part is how we prompt the model. We're asking it, how many solar panels are there in the image? The image is from a source and placement. Please explain your thoughts and then output the number in JSON format. This gives the model some context about what it's looking at and asks for structured output that we can easily parse. All right, let's dive into these examples one by one and see how Gemma performs when counting solar panels. I think you'll find some of these results pretty fascinating. So for our first image, we've got a drone shot of a roof with what should be just a single solar panel. But here's where it gets interesting. Gemma thinks it sees 6 panels. The AI describes several solar panels installed and mentions some are partially obscured by the roof structure and debris. What's happening here is pretty clear. Gemma is mistaking other rectangular features on the roof for solar panels. You know how roofs often have vents, skylights, or just differently colored sections? Well, without specific training on solar panels, Gemma is seeing these rectangles and thinking that must be a panel too. It's a classic case of false positives. Moving on to our second example, we've got another drone image, but this time the panel is in an open space rather than on a roof. And guess what? Gemma nails it. One panel in reality, one panel in Gemma's count. The AI correctly describes a relatively large, square-shaped panel mounted on a simple frame and placed in an open area. This success tells us something important. When solar panels are isolated and have good contrast against their background, Gemma has a much easier time. It's like asking someone to count apples on a plain white table versus asking them to count apples scattered throughout a messy kitchen. Context and clutter make a huge difference. Let's jump to example 15. We're back to overcounting. There are 115 panels in reality, but Gemma estimates 420. The AI attempts a structured approach, counting approximately 12 rows with around 30 to 40 panels per row, so 420 panels in total, a significant overcount. This substantial overcount of more than triple the actual number shows that while Gemma's row-by-column approach makes sense, its estimation of panel density is way off. It's like correctly counting the number of rows in a theater, but drastically overestimating how many seats are in each row. Better calibration on typical panel sizing and spacing would help improve these estimates. Now here's a pleasant surprise. Example 16 has 126 panels in reality, and Gemma estimates 130. The AI describes a large array and estimates approximately 121 for these solar panels. This is remarkably accurate, within about 3% of the ground truth. It seems that for this particular image, Gemma was able to correctly gauge the scale and density of the installation. This success case is valuable because it shows that accurate estimation is possible under the right conditions. The approach here, looking at the overall pattern and estimating a reasonable range, seems effective for larger installations. So what have we learned from all these examples? A few clear patterns emerge. First, there's a stark difference between drone and satellite performance. With drone imagery in examples 1 through 11, we generally saw overcounting, while satellite imagery in examples 12 through 18 gave us much more variable results, from dramatic undercounts to significant overcounts. Installation size also plays a major role. Gemma struggled most with single panels, often misidentifying them as multiple panels. Medium installations got generally overcounted too. But interestingly, some of the best performance came with larger installations of over 100 panels, where Gemma sometimes got remarkably close. The most common error patterns are pretty clear: mistaking cell divisions for separate panels, misidentifying roof features as panels, and inconsistency in counting methodology for larger arrays. The satellite imagery brought additional challenges with scale perception. Going forward, I'd focus on several key improvements. We need clearer prompting about what constitutes a single panel versus an array. We need different approaches for drone versus satellite imagery. We should adjust our prompting based on installation size. And for larger installations, a systematic counting methodology would help tremendously. The most exciting part: some of these examples show that Gemma absolutely can get close to accurate counts under the right conditions and with the right approach. With better prompt engineering, I'm confident we could dramatically improve performance across all these scenarios. And that's what makes this experiment so valuable. We're learning exactly what works, what doesn't, and how to make it better next time. In conclusion, Gemma3 shows promise, but isn't quite ready to replace human analysts for precise solar panel counting. However, it could potentially be used as an initial screening tool to identify properties with solar installations, which could then be counted more precisely by humans or specialized models. If you're interested in sustainability applications of AI or want to improve on these results, I encourage you to check out the Lacuna Solar Survey Challenge on Zindi. The applications go beyond just counting. Accurate solar panel tracking could help with energy production estimates, grid planning, and monitoring renewable energy adoption rates. That's it for today's experiment. If you found this interesting, please hit that like button, subscribe to the channel for more AI experiments, and drop a comment letting me know what other models or datasets you'd like to see tested. Thanks for watching, and I'll see you in the next one.